Let's talk about gradient descent. Gradient descent is the foundation of all machine learning. So if you kind of tune out of the class after this talk, I think at least hang around for this one, right? So our goal is to optimize an algorithm, any algorithm, to find a minimum cost. And we do that by iteratively updating parameters, right? So that's the key part here. We're just going to take a little bite of the data, bring a little bit of data into memory, and then walk through it. So idea is that we want to compute the gradient of the slope. I like to think about it as, think that you are up here and you are on a mountain, and the mountain is completely foggy, right? You can't see anything, but you can take a step. You're just going to take a random step and hope you don't fall off a cliff, right? And from that step, you can know, did I walk uphill or downhill, right? And if I walked downhill, maybe I want to take another step in that direction. If I walked uphill, maybe I want to take another step in that direction. I mean, not take another step in that direction, right? And then if I walk downhill, I can start to take a few steps and figure out, do I want to walk down to the left, down to the right, just kind of piece by piece. All I'm feeling at any given location on this map, on this mountain, is the gradient, right? So if I can calculate the gradient, I can take a step forward. Now, how big I take that step, that's called my learning step, right? So if I take a step forward, if I take a small step forward, if I take a big step forward, that's my learning step. And I get down to the bottom, and that's going to be my minimum. And that's the goal. The goal is to use gradient descent to get to the bottom. And we're just going to, compute the gradient, right? That's going to find the slope. You can also think of it as like you're just standing there and moving your ankles around, or just kind of moving your foot around, compute the gradient, find the best way. You take a step in that location, then you repeat and repeat and repeat and repeat till you get to the minimum. And that is, in and of itself, machine learning, illustrated by this cool little curve. Okay, your learning rate is very, very, very important, right? If I take a lot of small steps, I'm moving in the right direction. What's the problem? It might take me a very long time to actually get down the mountain, right? Not bad if you've got time and your computer's fast enough, right? So the obvious answer is, well, I want to take big steps, right? Well, what's the problem? So these steps here are the same amount of distance in theta, a little hard to see. And my first step gets me pretty close to the bottom, but not the actual optimum. And my next step, right, now means I'm going back up, right? So then what's my next step going to be? Because I'm here, I know I went up, I know my gradient's this way, my third step's going to be here, I went down. What's my next step going to be? Well, I knew that the gradient was moving down between those two lines, so I'm going to continue to move over here, and then I'm going to come way up here. So if you're just taking steps with these 3 data points, you will be forever circling around the optimal solution, right? And if you run this out to, if you continue to run this code, right, your error will look like this forever. So you can say, oh, well, I just take the, if you don't stop, if you don't get your model parameters at an exact point, right? If you just go to 500 and take the end, you might actually end up with these parameters. So if you have an ETA that's too small, right, it won't really converge. And if you have one that's too large, it'll take forever to convert it if you're too small. And if you're too large, you'll overshoot and you'll have a fair amount of divergence. Kind of in classical optimization theory, there's a couple other problems that one might have. You might have a system that's got a local minimum and a global minimum. And if you get stuck in a local minimum, there's not much you can do to get out of it, right? So I came down, I've got my learning steps right, and I end up in a local minimum, and I think that's my best answer. But really, you had a global minimum over here that you were trying to find. And then if you have a plateau, you might come down and say, oh, I keep moving, but nothing's happening. So I must be in an optimal space, right? And so that's just going to be kind of your classical plateau issue. So one, we won't go too deep into this, but one benefit here is that mean squared error is a convex problem, right? And so there's only one global minimum. So when we compute these mean squares errors, we just have one global minimum. So this won't be an issue for what we're dealing with. Your homework that's due Thursday next week is building out a gradient descent algorithm by hand for a mean squared error. So not using the sklearn, but actually like putting together the linear algebra to solve it out. So okay. For for gradient descent, there's a few different methods that we will go over today. Yeah, we can get through them all, I think. Yeah, we can get through them all. Okay. A few different methods that we're going to go over. We're going to go over batch, mini batch, and stochastic. So these are the three kind of big ways for us to tackle gradient descent. And there's trade-offs between all three. Pretty simple, right? And then that graph here will make more sense. But batch gives you this nice smooth line. Mini batch jumps around a bit, and stochastic just jumps around a lot, right? So, but each has a benefit. Okay, so before we go and talk about all these models, I thought that it's just kind of best to put them out here. So your normal equation, your closed form solution for a large number of m, right? Sorry, let's start with this. So your normal equation, if you want to do that in sklearn, you will just use the linear regression call. For stochastic gradient descent, you will use the SGD regressor call. If you want to do batch or mini batch, you can't actually do it. You can kind of tune the stochastic gradient descent to get you there, but it's a good way for us to talk about it. The normal equation for large M can be very fast. For large N, right? So for a large number of features is very slow. You can have a lot of instances, but you can't have a lot of features. Luckily, it has 0 hyperparameters for you to tune. That's nice. You just feed it the equation and you're done. Stochastic gradient descent can be very fast for large M. It can also be very fast for large N. Does it do it in memory? The answer is no. So it doesn't need enough memory to do it. So you can do it on a pretty small computer. But it does add hyperparameters to tune. It does allow you to scale, which is also nice. But, you know, if you get the right training, there's really no difference between these algorithms, right? Basically, it's how big your data set is and how long you want to wait. Okay, so the most basic form of this is batch gradient descent. And that uses the entire data set at each step, right? And because you use the entire data set, you have theta transpose x minus y, and you compute all of that to get your j, which are your errors, and j is the value that you're trying to minimize. You compute the exact next gradient, and it works really well, but it can be slow for large data sets, right? So the reason that sklearn doesn't have this in it is because you can just tune the stochastic gradient descent method to be able to ingest all of your data. But a batch gradient descent will ingest all of your data. So okay, so that gradient computation, if you want to compute your gradient, your d theta j, so your change in your parameter with respect to j is just this. 2 of m summation theta transpose for your ith instance, for your y instance, for your multiplied by k. If you put that out into vector form, you get this. So again, if you have a positive gradient, right, you want to move in the opposite direction of your gradient. So when you do the homework, that's just what you'll code in. And then using the full data at every step, right, can be quite slow. So again, if you've got memory big enough to use the full data at every step, you probably have enough memory to just do a closed form solution. So it's kind of an academic curiosity, but important nonetheless. So let's look a little bit at choosing the right update amount, right? So if I'm at theta, so when you write up your code, this is pretty much the equation that you want to write right there. I have the estimated parameters for each one of my model, the estimated parameters for each one of the parameters that I'm trying to get, right? So in my linear terms, theta 1, theta 2, which is just m and b and y equals mx plus b, multiplied by my step size, which is my learning rate, and then multiplied by my my gradient or my slope, right? And then multiplied by my error. So this will give me my theta value for the next one, and then I can continue to iterate through that, and in each time I can calculate the new error, I can calculate the new gradient, but my eta value stays the same. So if I have an eta 5e to the negative 7, I have a very small eta, and I'm trying to, I have a relatively large eta, and I'm trying to fit this data set. This is the Ames housing data set. And you'll see how this kind of looks like a rainbow, right? That's each step of me trying to converge on my model. So I coded this up by hand. I'm trying to fit the data set, and it's just shooting all over the place. I'm getting absolutely nothing, really, because my theta 2, because my theta 1 is my intercept, my theta 2 is just bouncing all over the place, right? So if I have a theta, kind of like Goldilocks and the Three Bears, that's 5e to the negative 9, and my theta is too small, I feed up all 10 iterations. And you can see here that iteration after iteration after iteration after iteration, I'm slowly starting to converge. And if I do 50 or 60 or 100 iterations, I'll get there, right? But I wasn't able to get there in 10. And then if I set it as 5 to the negative 8, I can pretty much converge perfectly on 5. And what you'll notice is that as I start out, I have big steps, right? And as I move, my steps get smaller and smaller, right? Because I've got the right learning rate. Does that make sense? So picking the right learning rate's pretty important. Okay, so now let's talk about stochastic gradient descent. I've got my instances, and I've got my features. What if I have a model and I just feed it one house, right? So I feed it one instance and all of the features, and I update my parameters. What will happen? I will update the parameters based on that single house, right? That's all I'm seeing. But let's just say I take one step. So I update based on one step, and then for the next step, I give it a new piece of data, and I update a new parameters. I'm going to be jumping all over the place, but the goal is, if I do this long enough, I should more or less kind of come to the average of all of them, and I only have to feed one house in at a time. It takes a lot of steps, but I don't need the memory to capture all of my features. So that's stochastic, random gradient descent. Update parameters using one sample at a time. Uses x of I and y of I instead of the full data set. So I just use one instance. And kind of, in that sense, it's opposite of a batch gradient descent. Maybe I don't like that. Faster for larger data sets. Ooh, I like this one. Enables online learning, right? Every time I have a new data set come up, I can update my features and I can move on, okay? And I could probably have an Arduino that continuously in real time, every time a house is sold, recalculates the average price of a house because the amount of math that's happening is actually very simple, right? So, might take you a while, but but if you're only feeding it one at a time and you only sell 10 houses a day in a small town, like that's pretty good. Um, okay, so here's your update rule. It looks very similar, right? Your theta next is your theta times your eta, which is your step times your gradient times your loss function for that one. The difference is here is I just have one instance, right? But mathematically, it looks very similar to the last one. Okay, so what does this look like? If I have a target in theta 1 and theta 2, and this is theta 1 value, theta 2 value that I want, and I run this in batch, every time I feed all of the data in, I'm going to get a nice iteration down, right? And if I run this, so here's another value that's like my error per step, right? Now, if I run the stochastic, it's going to jump around a lot, but it'll get there eventually, right? And also, my batch gradient descent is always going to reduce the error every time because I know what feature path I want to take. I know the gradient. And so I'm always going to move in a direction of less gradient. And then the stochastic gradient descent, I'm going to have my error come up, my error come down. Has anyone ever overreacted to an input in their life, right? Like you watch the news constantly and believe everything you hear. This will be very stressful if you're trying to watch this optimized going up and down. But if you understand that, oh, it's just kind of, there's a stochastic aspect to it that we kind of just embrace and let happen, it can work quite well. Okay, so that brings us to the middle piece, which is mini batch gradient descent. What happens if I just take half of my data, a third of my data, or I just take the 100 newest data points, right? Or 100 newest instances and I feed them in as a mini batch, right? So my update rule is going to be exactly the same, except now I have from instance I to instance I plus something. And I've got my same step function, my same thetas, and again, I'm just trying to get my thetas. So I've got mini batch, which is taking all of my data, doing every step. I've got stochastic, which is taking one data point at a time, and then we'll call mini batch something. With the right parameters, you can get the stochastic gradient descent regressor to just ingest all of the data in sklearn, so you can create a batch gradient descent, and you can also feed in more than one. It's not a true stochastic gradient descent, at least in the terminology that we use, because it can take more than one.